Okay, let's get restarted here. I'm gonna come back here. Okay, how are we doing? Good? Okay, good. Just want to say it's great to have you back. Very proud of all you're doing and all the work you're putting into this, and we're working on it together, right? Uh, so let's go ahead and come back here and let's talk now a little more about what about free energy and equilibrium. So basically, notice that we've been using, for these calculations we just did here, we're using standard enthalpies, standard entropies. We're calculating standard free energies. In other words, everything we're using has to do with substances in their standard states. But if you think about it, once the reaction starts, even if you're starting at equilibrium or at standard state, the reactants and products would probably move out of that standard state. For example, if we start the reaction at 1 molar concentrations, it is likely that those concentrations are going to change, right, as the reaction proceeds. So if you use a little more elaborate math than what we've talked about here, we can arrive at this equation I'm going to show you here, which is a more exact way of calculating the actual free energy of a reaction. And it looks like this. Okay, so in this case, of course, what we have is what we've been calculating for the most part has actually been the standard free energy change, delta G naught. So what we're going to do here is we're going to introduce a correction, another term into here, where R is going to be the gas constant. But this time what we're going to do is that liters atmospheres portion of it, we're going to convert it into units of energy. That's 8.314 joules. T is the absolute temperature. And remember, our good friend Q is the reaction quotient. Remember that we calculate the reaction quotient the same way we would calculate an equilibrium constant, except that we are not guaranteed that the product we get is going to be the same as equilibrium concentrations. So if we think about it, of course, at equilibrium, we said delta G equals what? 0, right? So if delta G equals 0, that means that we can rearrange this equation and find out that Q at this point is going to be equal to the equilibrium constant, because that's what Q is when you're at equilibrium. And if we substitute these values in the equation above, delta G is 0. Remember, delta G is the actual free energy change for the reaction as is. Delta G naught is just under standard conditions. And we're saying, no, we're not in standard conditions here. Instead of Q, we put in K, and we can rearrange this expression to give us this beautiful equation here. It gives us the connection between the standard free energy change of a reaction and the equilibrium constant. Right. So let's look at this equation we just derived here. And let's paint a couple of scenarios here. What is the equilibrium position based on delta G naught? If the standard delta G is negative, well, that means that the whole thing on the right has to be negative. That means that log of K has to be positive, and therefore K has to be, that's right, bigger than 1. In other words, if delta G is negative, at equilibrium, the products are favored. Remember, don't get delta G naught mixed up with the actual delta G. The one that tells us that the system is at equilibrium is delta G. So if I were at equilibrium, delta G would be equal to 0. That doesn't mean that the standard free energy change has to be 0. It may be negative. And in this case, what's happening is products are going to be favored at equilibrium. Now, let's say that the standard free energy change is positive. Again, remember, that doesn't mean that under the conditions we're looking at, the overall process has to be non-spontaneous. This is in the standard states. If this is positive, then that means that something has to offset that negative sign on the right side. That means that log of K has to be negative. So you have a double negative here. For the log of something to be negative, that means that that something has to be less than 1. And of course, for us, a small equilibrium constant indicates that the reactants are favored at equilibrium. Okay, so in other words, if we know the standard delta G of a reaction, we can predict at equilibrium which side is favored. What is the position of equilibrium for that reaction? It's pretty cool, huh? The second thing we can do with this equation is we can decide, you know what, there are some situations under which I may have to switch the way I measure values. For example, let's say that I'm studying a chemical reaction that has a very, very small or very, very large value of the equilibrium constant. Let me give you an example. This reaction here that I'm showing has a Kp in the order of 10 to the negative 31. Now imagine that you tried to measure the concentrations or the pressures of the species so that you could find out what Kp is. There's no way that you're going to be able to get pressures accurately measured for that product to give you a Kp that's that small. That requires a tiny, tiny, tiny partial pressure of the NO, the nitrogen monoxide. So if you want to find out what Kp is, what you can do is you can go in and using the standard free energies of formation, you can calculate the standard delta G and then use this equation on the top there to solve for K. Now let's say that the equilibrium constant is of a reasonable size. For example, this reaction that I'm showing you here has a Kp that's approximately 1. Well, in this case, you know, it is possible because the values of the pressures here are going to be within reach of our measuring instruments. It is possible to measure the equilibrium constant and then use the equation there on the top to calculate delta G naught. So you can see where this equation allows us to calculate one when the other one might be easier to measure. All right. All right, so let's go ahead and do a little practice exercise here. Let's set this up. I have a reaction here. And we have the standard delta G for this reaction. And we have in an experiment, what were the measured pressures at a given point in this experiment? Okay, so let's go to our whiteboard here. There we go. And again, I'm sorry that my internet connection today is not very good. Let me take this from underneath. Okay, let's set it up properly here. Okay, there we go. So now we're going to solve this problem here. So here's the equation, right? So delta G is delta G naught, standard delta G, which in this experiment is 2.60 kilojoules per mole. Okay, plus R, which is 8.314 joules per mole per Kelvin. The temperature, hey, they didn't tell us what the temperature was. Well, since they don't tell us, is assume, in the absence of any other information, assume that the temperature is 25 degrees Celsius, and that equals 298 Kelvin. Okay, I'm hoping you remember how to calculate Q, right? Remember, Q is products over reactants. So in this case, that would be, since they're giving us atmospheres, it would be the pressure of HI squared, because there's a stoichiometric coefficient of 2 there, divided by the products of the pressure of H2 times the pressure of I2. Let's see under these conditions what that is. So the pressure of HI is 0.23, and we're going to square that. The pressure of hydrogen is 4.26 atmospheres. And remember, when we calculate any form of equilibrium constant, including the reaction quotients, we're not concerned with units. Iodine is 0.024. And remember, that has to be taken a log of. So it'll be 0.23 squared divided by 4.26 times 0.024. All of that. You know what? I'm going to let you guys work a little bit here on the equation. Give you a few seconds to get your calculators out and do a little calculating. All right. Okay. So what I think we're going to get here is, when you do all that, is that delta G. And again, you probably needed to convert the joules to kilojoules or the kilojoules to joules. Okay, so I think that you're going to get something like 0.97 kilojoules per mole. I think that's what you get. So if that is delta G, and delta G is positive, right? We know from the value of delta G naught that the equilibrium here tends to favor the reactants. And as you can see, even under these pressures, what you have is you have a positive delta G. In other words, the forward direction is non-spontaneous. That means that the reaction will proceed towards the reactants, towards the reactants. Very good. So now you know how to solve all these kinds of cool problems and stuff, right? Well, I want to take you through another exercise here before we part company. Well, let me give you a few more seconds to kind of like write this stuff down. Let me straighten that up. Okay, I want you to consider the following. I'm going to pull. Don't worry, I'll have these things scanned and I'll put them in your Canvas page where I put the video of the lecture. We're going to derive something called, sorry, choking here, the Van Hoff equation. Okay, so what is delta G naught? We have two expressions for it, right? One of them is, it is minus RT times the natural log of the equilibrium constant. But if we consider the equation from the second law of thermodynamics, what we have is this would be the standard delta H minus T times standard delta S. What if I take this and I divide both sides by negative RT? So I'm going to divide by minus RT. So this one minus RT. Oops. So I get on the left side log of K. On the right side, I'm going to rearrange this a little bit. I'm going to put it as follows. I'm going to say it's delta minus delta H over R times the reciprocal of the temperature. So I'm going to separate these two factors here. And over here we have plus, because we have a double negative, and the temperatures cancel out. So I would have delta S over R. And my friends, can somebody tell me what that looks like? That's right. It's the equation of a straight line, where X is the reciprocal of the temperature, log of K is Y, and this guy here is the slope, and that guy here is the intercept. Pretty cool. So that means that if I had a set of data and I could do a plot of the log of K, natural logarithm, of course, versus the reciprocal of the temperature, I would get a line. Let's say, for example, I get a straight line like this. And the slope of that line would be delta H, minus delta H0 over R. Since R is a constant, I can use this to calculate or to find what is delta H for this process. Right, now be careful. This is negative. And also, we can see that the intercept, of course, this is not going to get here because there's no such thing as a 1 over T cannot be 0. But if you expand it, if you, what's the word, project it out there, extrapolate, I'm sorry, extrapolate is the word I'm looking for. The intercept here would be delta S naught over R. So you could use it in theory to find what is the value of delta S. So this is called the Van Hoff equation. In your experiment this week, well, let's call it your lab activity this week, you are going to have a chance to do one of these. We're going to give you some data. You're going to plot
Professor.
out this, and you're going to be finding all the different things in here.
Hey,
Okay.
Professor.
Somebody
Hey,
trying to tell
yeah,
me
it's
something.
me. It kind of looks like. Could you also do a Pythagorean theorem with that?
Well, you mean like make this into a
Yeah, a triangle.
triangle and do that? What would that give you though?
I don't know. I just saw the pattern. I just glanced at it, and that's what I saw. I don't know.
Yeah, it you can do that, but it doesn't help you because it doesn't give you useful data to apply the the theorem here. You know what I'm saying? So that's mostly for calculating what is the length of this thing, but we're not interested in the length of these things. I mean, if we knew the angles, we could calculate from sine and cosines what the values are, but what really helps us is the slope and the intercept of the graph. And let me give you another way of looking at this, if I can find a piece of paper that will work. Hold on a second, let me get another piece of paper. Many times when you are dealing with these kinds of measurements, it's not really that feasible to get a whole list of temperatures and equilibrium constants and all that kind of stuff. So unlike the lab that you're going to be performing this week, your activity, sometimes you can only get 2 points in here. So let's do a 2-point derivation of this and see what we can do with it. Where's I lost my edge here. Let's do a 2-point derivation. And you'll see where I'm heading here in a moment. Let's say that you have the equilibrium constant at 2 different temperatures. So let's say K2 versus T2 and K1 versus T1. So let's write out the equation we just derived earlier. So this would be minus delta H naught over R over 1 over T2 plus delta S naught over R. We make the assumption that the standard enthalpy and the standard entropy changes are constant, right, over this range. Let's do K1. Log of K1 would be minus delta H naught over R. That's 1 over T1 plus delta S naught over R. And let's say that I now subtract the second equation from the first one. So over here, I would have, I'm going to kind of put it out here. So this would be log of K2 minus log of K1. Now, these two guys have a common factor here. So it would be essentially minus delta H over R. And inside you would have, well, this minus that would be 1 over T2 minus 1 over T1. And these two guys are going to knock themselves out because they're the same. So what I like to do is express this in a more compact way. When you have the logarithm of something minus the logarithm of another thing, that essentially is the logarithm of the ratio between them. And over here, we would have minus delta H over R times the difference between the reciprocals. okay? Or in some cases, it's difficult to do reciprocals like this. For example, in my calculator, I would have to do this, put it in memory, then do this guy, then subtract that, and then continue the rest of them, which is kind of annoying. So you can actually convert this algebraically, because the way you would subtract these is by finding a common denominator, which would be the product of these guys. So this is another way of writing it. K2 over K1 equals minus the delta H standard. And then you can put it as T2 minus T1 over T1 times T2. So any one of those two expressions will work for us to do some kind of calculations. Cool. Okay, so let's do a little practice here. Let me pull this up a little bit, if you don't mind. Let's do a little practice. Let's say a reaction. Oops, running out of ink here. A reaction has K1 equals 4.63 times 10 to the minus 5 at 25 degrees Celsius. If its standard enthalpy change is 58 kilojoules per mole, what will be the equilibrium constant at 65 degrees Celsius? So I can fix this a little bit so it looks a little nicer. That didn't help much. So let's use this expression we just had here, right? So notice, let me ask you this just before we go on. We usually expect temperature to favor, cause a reaction to be favored, right? It increases the forward rate. So we expect typically that at higher temperatures, K is going to have a higher value. You can look at that equation we just saw there. Of course, a lot of it depends on delta H and delta S, but in general, we see an increase in the equilibrium constant at higher temperatures. Of course, unless the substance begins to decompose or something like that, but we're not going to deal with that right now. So let's just fill in the blanks here. So this means that log of K2 over K1, which is 4.63 times 10 to the minus 5 equals minus, well, we have to put in here the value of delta H. That'd be 58. Actually, you know what? I made it wrong. This is 58.0 kilojoules per mole. Don't forget to write these units, okay? And R would be 8.314 joules per mole per Kelvin, or per Kelvin per mole. So that means we need to convert these either to joules or kilojoules. So let's say essentially there are 10 to the 3 joules in 1 kilojoules, so that we can cancel those out there. And you can see the joules are going to cancel out, the moles are going to cancel out. Essentially, we should end up with no units, because remember, the log of something without units should not have any units. All right, let me scoot this over here a little bit. And now let's put in the rest of the expression here. We had to convert the temperatures to Kelvin. So 25, of course, is 298. But 65 plus 273, that's 338. So this will be 338. Oh, guys, you know what, guys? I made a mistake here. And nobody told me. Nobody told me this. I changed this around, right? I changed it around. So I had to switch that out. So this is not negative here. I did it precisely to avoid the negative sign, and then I forgot to take it out. My bad. 338 minus 298, right? And this is going to be Kelvin. And in the bottom, we have 338 Kelvin times 298 Kelvin. Close the parenthesis. So one of these Kelvins is going to cancel here, and the other one is going to cancel with this one over here. So we got rid of all the units. That's why I told you to write the units down, because that's your kind of like your bottom line check, right? That's where you make sure that everything makes sense. All right. Well, I don't want to take up so much of your time. You've been very patient already. So log of K2 over 4.63 times 10 to the minus 5. All of this thing here comes out to be 2.77. So that means that K2 is going to be 4.63 times 10 to the minus 5. Oops, I lost my space there, sorry. Times E to the 2.77. Hopefully your calculators can do that. And according to my numbers here, this should come up to be 0.074 or 7.4 times 10 to the negative 2. As you can see, at the higher temperature, the equilibrium constant also became larger. Again, my apologies for forgetting to arrange this. I forgot that I had switched things around here. All right, let me give you a few more moments to process that. Okay, so today we explored this property of the free energy change. First of all, we learned how to calculate it both from thermodynamic data that gives us the standard free energies of formation. And so we can simply say the free energy change for a reaction is the free energy changes of products minus the free energy changes for the reactants. And we can get that from a table. We can also calculate delta G if we know the enthalpy change, the temperature, and delta S. And that equation allows us to make predictions as to whether, given the dimensions, I guess better said, the signs of delta H and delta S, we can predict if the reaction will be spontaneous or non-spontaneous and under which temperature conditions. And we can pretty much calculate if a reaction is non-spontaneous and there is a way, temperature-wise, of turning it around, we can calculate what is the threshold temperature at which we can switch a reaction from being non-spontaneous to spontaneous, assuming that it can be done. And then in the second part of our lecture, we saw how there's a direct connection between the standard free energy change and the equilibrium constant. And this allows us to do several calculations in terms of what if the system is not at equilibrium, what if it is at equilibrium. And then we derive these equations for the Van Hoff graph or Van Hoff plot, and also for the 2-point relationship. If we have the equilibrium constant at a given temperature, we can calculate what is going to be the equilibrium constant at a second temperature. And of course, we can also calculate, well, at what temperature will the equilibrium constant be, let's say 4 times what it was originally. So there's all kinds of problems we can solve there, okay? So I guess we don't have any more questions. What I'm going to do is we're going to stop here. And then when I'll be here back at 7, and I'll leave it open in case anybody wants to ask questions. I don't have anything to give you. I don't have any review, any problem sets, nothing like that. It's just if you have questions that you want to be here at 7, you can join me again, okay? So we're going to pause right here.